Okay, so it's not like we're going on to a new area of physics. You guys basically, what was the first chapter all about? Somebody tell me. First chapter.
Uncertainty.
Uncertainty was a big theme. What else? Units was a big theme, and how to all kinds of different variations on those. Those are the two big themes, I think. Second chapter was about what?
Motion, one dimension.
Motion, and what do we call motion in physics?
Mechanics.
Mechanics, right? And it was only, Jake said, limited to what? One dimension, and we had some kinematic equations which described motion in one dimension. Those same equations apply to 2 dimensions, which is what we're going to do now. It's just when we're in 2 dimensions, we have to also think about vectors, okay? So I think today mainly we're going to focus on the math of vectors. For a lot of you that's review. For some of you, you haven't seen much vectors, so either way I don't think it matters, okay? So we'll do the math part mainly today and maybe one application problem, and then tomorrow we'll do a bunch more applications. And you'll be set to start the chapter, but I'm not going to say this chapter is due till maybe next Thursday or Monday. Okay, so you have a lot of time to work on it. This is a big chapter. I would say of AP problems, the ones I saw, this is probably the heaviest thing on the entire, this and the next chapter on that entire AP exam. Okay, so we don't want to shortchange it. Okay. Okay, so what is a vector? Can anybody tell me? Jake.
Quantity that has direction and magnitude.
Yeah, you know it from Despicable Me. The villain's name was Vector, and it says it's because I have direction and magnitude. Many points, right? Because vectors have direction. So vectors can be expressed in different ways. A lot of the time they have like a little hat guy on them like that. If you see a bold letter, a lot of the time that means that's a vector quantity. And then you also just have to think about, is this a vector or not? Does it have direction and does it have magnitude? If so, it's a vector. Okay? The length or magnitude of a vector has a notation too, so the length or magnitude. And there's different ways to express that. Different books use different ones. Sometimes they use 2 bars. Sometimes they use 1 bar. Usually the length or magnitude is going to involve what kind of mathematical operation? Square root. That's how you find it, right? You use the square root. And then what goes inside that square root? Anybody know?
The squares of its components.
Yeah, I think it's components, like the horizontal component squared plus the vertical component squared. That's how you find the magnitude. Okay, so it's real simple to find. And that's, where do you think that comes from? This is equal to the magnitude, right?
Pythagorean.
It just comes from the Pythagorean theorem. It's so simple. It's just the Pythagorean theorem in short. If you're in 3-dimensional land, you're a vector still, right? 3 dimensions, how's the magnitude going to be affected? You're going to put plus VZ squared. If you're in 4-dimensional space, wherever that is, I don't know, you just put another one in squared C. So vector magnitude is real easy to do. Okay, so I think we're just going to talk about some of the book's examples. So it says, in the first example that we're going to consider is, let's say we have 2 vectors. They each have magnitude 3. So let's write that down. Let's say we have vector v and vector u. Their magnitudes are both equal to 3. So you've got 2 vectors floating around. If you add them together, what's the most their sum could possibly be? If you have vector u and then vector v, you add them together, what's the most their sum could have? And how would that look? It'd be like straight and then another straight, and you do the square root thing or whatever, but the length of that would be what? 6. What's the least their magnitude could possibly be? 0, and how would that look? They'd be, if they were completely perfectly in opposite directions. So if you had like v going like this, and then u going like that in the perfect opposite direction, how much displacement occurred?
0.
None. And displacement is vector magnitude. Okay, does that make sense? Displacement, you might write that down. A way to think about displacement, it's not the only way, but it's a good way. Displacement equals vector magnitude. If you have like more than one vector and you're adding them together, the total net displacement will be like the magnitude of the result. We'll see some problems like that in just a minute, okay? I think I'm getting ahead of myself here a little bit, but that's okay. So notice up here, if this was our u and this was our v, where's u plus v? The vector u plus v, what's it look like? That is u plus v. Yeah? So over here, what's u plus v look like? Well, it's like that, but then it takes itself back and it doesn't really have much of an appearance, does it? But that's how you do it visually with vectors. You add them together. Otherwise, to add them together by components is super easy. We'll just wait for some problems to do that. It's so easy. Okay. Let's see. So what if we didn't ask that? What if I asked, okay, not how can you make it the most or the least, what if they're perpendicular? We said, what are their lengths in this example? 3. Their magnitudes are 3. What if they're perpendicular? What is the magnitude of the result now? So this is u plus v, isn't it? So what's the magnitude of u plus v?
Also 3. 3 root 2.
Well, it looks like it has some dimension, doesn't it? Don't make this hard. What did I draw there? What kind of shape is formed? A triangle. What kind of triangle? A right triangle. So what can you use? Pythagorean theorem, which shortcutted is going to turn into what we just talked about. Yeah? 3 squared plus 3 squared, which is going to be what? Which we might have as 3 root 2. Either one of these is fine, yeah? Okay. Let's see. So I've been saying the word components. Let's get that out there a little bit more clearly, I think. So I've been saying it. You guys have been saying it. Some of you knew about them. Some of you probably don't know about them. That's okay. So a vector can always be expressed as the sum of 2 component vectors, and that's in my notes. Yeah, so if you want to write it down, fine. But a vector can always be expressed as the sum of 2 components. So in other words, the whole vector in symbols, you might write, try to put that on there, right? The whole vector can be expressed as Vx, its x direction, its horizontal direction only, plus its vertical direction. And that's always true, okay? So let's just consider any old vector and see what I'm talking about as a picture. So there's vector v, right? What do I mean with this horizontal and vertical business? What's the horizontal component of v look like? You could draw it like this, couldn't you? That is Vx. That's just the horizontal part of what it accomplishes as a vector. Does that make sense? Questions? So what does it accomplish vertically in terms of displacement? It moves you from here all the way up to that high, right? So that's how much vertical direction the vector moves you. So those are the horizontal and vertical components. Of course, vectors don't just have length or magnitude. What else do they have?
Direction.
They have direction. How do you express the direction? You can see it's pointing that way, but how do we say that with math? We give an angle of some kind. And usually you reference that from the positive x-axis, right? Just like we've always done in trig forever and ever and ever and ever. Okay, so that's the direction. Let's see. So then if we were going to write, once again, the magnitude of v would be square root of vx squared plus vy squared. You can see it comes from the Pythagorean theorem. Nothing harder than that, right? This is a right angle. How would you get the angle if you needed it? Let's say you knew these guys, but you didn't know the angle. You need to know which way this goes, which way the vector's going.
Inverse tangent.
You could use like inverse tangent. Sometimes you could use an inverse sine or something too, right? But let's say we're working with the components only, and you'd go the inverse tangent of, how's tangent go? Opposite over adjacent, so Vy over Vx. So that's just a formula, and physicists a lot of the time treat that as a formula. Don't treat it as a formula, it's just basic trig, isn't it? The tangent of theta is what? Vy over Vx. Take the inverse tangent on both sides. There you go, there's your angle, so easy. Okay, so don't make that hard. What I also wanted to say though is, you can also express the components another way. So Can somebody tell me how else you could express the horizontal component that I have there? And this is really key. Can't you just say the magnitude of the vector and multiply by the cosine of the angle? That's a way you can come up with the horizontal thing. Can somebody tell me why? Anybody got ideas? And likewise, what do you think you can, how can you get the vertical?
So cosine of theta is dx over the magnitude, and if you multiply the magnitude over.
Should I write it out? Okay, Todd, you tell me what to write. So I'm saying these are two big time important equations. If you just want the horizontal part of a piece of motion, or you just want the vertical part of a piece of motion, there's how you do it. Now why? Why does that work?
So cosine of theta
So he's looking right here, right?
is dx over magnitude, because it's adjacent over.
This is just the magnitude of the vector, isn't it? We're thinking how long is that piece? Cosine is that, right? Adjacent over hypotenuse. And then you just rearrange it. If you want this part, if you just want the horizontal part of the motion, you just say, well, multiply that up on the other side. There you go. Now you have an expression for the horizontal part. Same thing with sine. If you take sine, you're going to have an expression for the vertical part. Questions? Some people okay, some people not. It's just looking at that and taking the cosine and sine. The nice thing they tell you is now you know how you can get just horizontal and how you can get just vertical for anything that moves. Does that make sense? Hope so. Okay, so let's look in our book. Let's open to page 52, because I don't want to write all kinds of stuff down on the board. Okay, page 52. I'm going to have to grab my book.
Yeah, it's so cool.
Somebody let me borrow theirs. Okay, so let's look at, I wanted to look at example 3.2. So it says, a rural mail carrier leaves the post office and drives 22 kilometers north, right? She then drives in a direction 60 degrees south of east for some more distance. What's her displacement from the post office? So how can we draw that?
22 going up.
Okay, so 22 going up, you guys agree? That's north? We'll put it in the coordinate system in a second. Yeah, then where'd she go? South of east, what do they mean? Like, okay, she's right here. Let's like draw a horizontal to get her bearings.
So it would be south of the
So
right
south
side.
of east, which way is east?
The right.
That way, so 60 degrees like that. Is that what she's saying? And then for how long? 47? So this guy's got to be pretty long, doesn't it? It's got to be longer than that other piece that was 22 kilometers. Is that what they said? Now they're asking, here's the post office where she started from, right? The post office. The question was, what's her net displacement from the post office? Can you guys see where that's at in the picture? The displacement is how far away is she from the post office. That's the net distance she's traveled from it. Yeah? So you can see, I think, that that's from right here to wherever the end of her route was. Right there. So the question is, how big is that piece? Did they ask us in what direction too? I can't remember. We'll just give it to them anyway. Might as well, right? So how can we do that?
Find the magnitude of that piece.
Right, but it's not a right triangle, so we can't just use like a little bit of trig, can we?
Add the x components and add the y components.
You guys hear Paul? Paul's saying if we had the x components, we could put them together and get the x component for the question mark. If we had the y components, we could get the y component for the question mark. We could also do other things, like maybe the law of sines or cosines. That might also work, but vectors are so much easier than that. So here's what we're going to do. We're going to say, let's call this v. That's a 30 degree, yeah. Yeah, we can put that in there if you want. Yep. Okay, so I want to express v as a vector. Now the book's notation is like vx plus vy. You can use that notation if you want. I personally like to think of it as vector notation. When I express vectors, you can say a vector is vx plus vy, or you can say a vector is, and use these vector braces and put the x component there and the y component there. I like this better because it feels like points. It feels a little easier to me, but it's up to you. Physicists like this, I don't know why. Anyway, so I'm going to go like that. So the question is, how can we fill these in? Because if we had those, didn't we have a thing a second ago that says the magnitude of v is the square root of those things like squared? That's all we've got to do. So the question is, how can we get v? And Paul told us how. So to get v, we've got to think, how can we get the vector there? So the x component of v, what's it going to be?
So are we saying
Is
the
this-
post office is the origin?
Yeah. Think about the origin right there. That's a good point. Yes, this is the origin. I guess I could have drawn it over again. I got lazy. So that's the origin. Does this move any in the x direction for that part? No. Does this move some in the x direction? Can you see it like this part right here? Does it go in the x direction?
Yes.
Yeah, it moves a certain amount. It moves, in fact, this far, does it not? So how did we just learn we could express that far? Its magnitude? What's its magnitude? What's the magnitude of this vector? 47. And then we said to get just the x component, you do 47 times
Cosine.
the cosine of the angle.
Maybe 60?
I think 60 would work.
Should we do negative 60, 60, what?
Well, either way, the x component is going to be the same.
It's really negative 60, isn't it? Now, the physics book doesn't like to show this stuff because it's not good for whatever reason. I'm going to put a negative 60 in there, though. Think about this, though. The cosine of 60, how's that compared to the cosine of negative 60 for math?
Just the same.
It's the same thing, isn't it?
The sine.
If you're in this quadrant or this quadrant, does cosine change? Cosine is x, right? Cosine is positive in both quadrants. It's going to be the same thing. So what is that? You can give me with your calculator.
44.7.
0.76, okay. So that's what we wanted right here. That's how much it goes in the x direction. Now the question is, how much does it go in the y direction? Well, does this go in the y direction any? 22, right? Does this go in the y direction any? It looks like it's going down, right? But how are we going to show that? All we need to do is the vector's magnitude times what? Sine of the angle, which you guys told me was negative 60. Very well. Very well done. Now you guys are saying, but wait a second. Doesn't that other vector go down? Shouldn't that be negative? What's the sine of negative 60, though? Do your calculator if you don't know. We should all know, though.
Root 3 over 2.
Negative root 3 over 2. It's negative, so that's going to be negative, which is what we think, right? This is going down, is it not? So it should be negative, if that makes sense. So, yeah, this would be 22 plus 47, negative root 3 over 2 from your unit circle or from your calculator. What do you get total? Somebody tell me. Like 60. I actually don't know. I think it's negative. Think about it. It goes up that much, but then it comes back down this much. Shouldn't the net y be negative? Should it not? You guys know what I'm saying? Should be, so does that turn out to be negative? Make sure you're in degree mode. Calculators, go, I'm not doing it. I have it in my notes. No one wants to say?
That's what I had, negative 3?
What is it?
Negative 18.
You guys agree?
Yes.
Negative 18.7, okay. Negative 18.7, so that's a little bit up there. Okay? So there we go. And then we say to get the magnitude of any vector, if we have its components, what do? You go the x component squared plus the y component squared, so you take the square root of 44.76 squared plus negative 18.7 squared. Make sure you use parentheses, and what do you get?
I think the 44.76 is wrong. Seems a little bit too close to 47.
Does seem a little bit too close to 47. What happened? Do this again. I don't have my calculator. I'm going to do it. I don't trust it.
I think it's 23.5.
Yes, that sounds like it. Somebody have radians on instead of degrees?
23.5. That's what I got.
Yeah, that was just a calculator error, yeah. But you notice, how did Paul pick up on that?
Just doesn't look
Just
right.
thinking about it.
There's no way. There's no way it could be that big. It's got to be less. Is that 23.5?
Yes.
What do we get for the overall magnitude of that guy? I'm going to use 30.0. Is that right, significant digits wise?
We could have two.
I should probably just use 30, shouldn't I? 47. Yeah. Units? Kilometers. Because that's the length of that blue thing, which is also what they asked us. They asked how far away is she from the post office. That's how far she is. Alrighty. Let's try another one. We'll just do one more today, and then maybe you guys can look at some problems. That's what I'm thinking. Maybe two more. Okay, let's look at 3.3 on the next page. This time it says an airplane trip involves 3 separate legs with 2 stopovers. And they want to know basically how far did the plane go? What was the plane's ultimate displacement? Yeah? So there's 3 different paths that the plane takes. So you guys tell me, what are those different paths? I think we'll just start from the origin this time and go from there. Yeah. Where does it go first?
Due east for 620 kilometers.
Okay.
Straight.
So straight this way. 620. Okay.
Southeast at 45 degrees.
South of east. We just did that, right? So this is 45 degrees for how long? 440. That looks about right. Remember, I'm trying to draw the vectors to be the right size. About. Next.
53 degrees south of west.
Okay, what's that mean? 53 degrees south of west. I think the best thing to do is probably go like that, so we can get our bearings again, right? We're right here, south of west. So that's like it turned this way, isn't it? And what was the angle they gave us? 53. So should this be 53 or that be 53? Where my finger is, right? No questions on that? We're okay? And then is that it, or?
It's 550 is the length.
Oh, 550? Should I make it a little longer? I think so. A little longer. Okay, so that's 550, and that's it. So then the question was, what was the plane's displacement? How far is it from home base, essentially, right? Here's home base. So we're trying to figure out how long is this vector. Who knows why it did that? Why would the plane have possibly done that? I mean,
Had to avoid a storm, maybe.
maybe avoid a storm. Why else?
Stop at multiple airports.
Yeah, maybe it had like some people were going to Chicago and then some people were going to Boise and then, I don't know. If I say a third one, you're gonna know I'm lying, so. Okay, so how do we do that? I think we can just express, just like last time, let's express each one of these three vectors in components and then just add them up. That's it. That's how easy vectors are. So the first one, let's say, I'm going to label it D1, distance 1, okay? You can use the book's notation or you can use mine. I like to just go like this, okay? What's its x component, guys? It's easy. X direction, what did it do? It went 620. Y direction, what did it do? Didn't move. There we go. Should put some vector guys on those, okay? D2, that second leg of the journey, how can we express it with x and y? X, does it move some? Yeah. 440 times the cosine? X is cosine, right? Like this isn't so much different from trig. X is cosine, X is cosine, X is cosine. How many times do I have to say it? Okay? Cosine of what? Is that 45?
No,
No, it's 135.
You could, right here, for this is our origin, it's negative 45 degrees, isn't it? Or you could go all the way around the circle and say 300 and, is it 15, I think? Yeah. Yeah, 360 minus 45. Yeah, but you could do that either way, right? So you could put cosine of negative 45 or cosine of its coterminal angle way around the circle, okay? Totally fine. I hate it when physics professors used to never say that to me. I'm like, what? Did I do it this way? They're like, oh, no, no, no. 440 times the sine of negative 45, or 315, whatever you like best. So then we get that with our calculator, right? Let's do that in a second. Let's do V3. The third leg of the journey. What should we do for that third leg of the journey? Of course, we're going to use the magnitude, but what do we multiply?
You just got like so many memories.
John Hamler and Shannon Mitchell.
What do we multiply by for the x? It's obviously going to be negative, isn't it? Like this part right here is going backwards, kind of. So it should be negative when we get our answer. Cosine of what? Careful. Think about where that 53 degrees is. You could go 180 plus 53. I like Jessica's strategy. Think about this as, see, I have a pseudo origin right there, and you can think of it like it's like in what quadrant, kind of? A third quadrant. Somehow you've got to say third quadrant. How you say that's up to you. You go 180 plus 53. What's that? I like that. 233. How else could you do it? Yeah, you could do like negative 127, something like that. Yeah, you could do it however you like. But somehow, remember, that angle is telling you what direction to go in. If you don't tell it the right quadrant, you're going to end up in the wrong quadrant. So somehow you've got to identify that I mean over that way. Yeah? So that should make sense. Okay, let's get our answer and make sure we don't make a mistake, right? It should be quick and simple if we made a mistake. What are these things? Calculator, gurus.
Do you want to do D2 or V3 first?
V2.
V.
This one.
Oh, D2.
I think I changed my names.
You did.
Okay.
Bad. My bad. I'm sorry. I'm trying to confuse you guys. D2. Let's do D2 first.
So the cosine would be 311.1.
0.1.
2.
Okay.
And then the next one would be the negative 311.12.
Okay. That makes sense because 45, 45. They're the same magnitude. Okay. This part.
And then for that one, it'd be 330, negative 330.99. So you could do 3.
Okay.
And then negative 439.24.
You guys are making Matt do all the work. Does that make sense? Okay, look at D2 again. Should it be positive in the x direction?
Yes.
Yes, it looks like it goes to the right. Should it be negative in the y direction?
Yes.
Yes, it looks like it goes down. Okay,
Yes.
D3. Does it go left? Yes. Does it go down? Yes. I think we're probably okay. So now what do we do to get the resultant? This is what you call the resultant vector, the green one. G. Yeah, you just add them all up, but go by components. So what am I going to put in here? I'm going to put 620 plus that plus that. Tell me what that is. It's got to be like 600 something, 500 something. 500 something. Let's see if it's stick up.
Nope. 600 more.
600 and
Oh no. I don't know, I'm just doing it in my head. No, we have heads for a reason.
613.
Yeah, to look at the count. I think there's 600.
I have 600 in my answer. If you do it exactly, you get 600.
13.
With our rounding here, though, what do we get? 0.1?
Yeah, 0.13.
That's just because of rounding, though.
I actually just didn't round it. I'll just put it in the cosine of it.
Okay, but remember, we're going to take care of that with significant figures, so it doesn't matter. How about this? Add the y's. Oh, negative what? She obviously went down. I mean, excuse me, the airplane obviously went down a lot.
Negative 750, 36.
Okay, but that doesn't tell us how far, right? That just tells us a vector representing where we ultimately got. Does that make sense? That is a vector representing where we went. How far did we go? Vectors are so nice. I love them. They don't just represent motion, they represent electricity, heat, everything.
960.81.
560?
960.
You guys agree? 0.1?
81.
What should I put for units?
Kilometers.
Those other ones were kilometers. And if we were going to be more correct about this, where would I erase?
We had 0.81.
0.81.
And then the 0.
So maybe we could move that to like
Or
961.
Yeah,
961.
Yeah.
I think so.
About 960. Because there's only two significant figures.
That's the, see, this is where it gets a little bit sneaky with the significant figures, which isn't going to be a big deal for us. Like, I'm not going to mark you wrong on a test, right? And I don't think AP will either. But if they included that zero like that, you got to think about, did they actually measure to that, or did they not? Think about it. If this is just a person, this is a person in an airplane, right? Do you think they actually measured 620 exactly? Probably not. So what do you guys think? I think Todd's right. I think we should probably go just 960. You got to think like that, though. You see what I'm saying? I don't think that they measured it that precisely, unless they used a computer. Then maybe. I don't believe the pilot is able to do that,
Use their
though.
flight computer, actually.
That's true. Maybe they just have it locked in cruise control. That's true. I guess you're right, Jake.
Who knows?
That sounds like that's what would happen in reality. So. Okay. I'd like to do one more. That's a little bit more physics-y, if that's a word. I don't think it is. Let's do one that's more like what is really important in this chapter. Or should we save it till tomorrow? I don't care.
How much time do we have?
We have like 25 minutes.
Is it gonna apply?
Why would you say
tomorrow?
we're good either way?
I'm just trying to help make a decision, Todd.
Let's do
appreciate
it.
if you guys would lower your voices.
It's my voice is too quiet.
Let's do it. If we can get this mostly knocked out this week, we'll have a lot of time next week to talk about problems, get this really mastered. So 3-4, let's look at 3-4 in the book. And I think again, I've done this fairly differently. At least it looks different. It's on page 57. So have a look at what's going on there. Let's just read the question and look at the picture real quick. So this time it says you're diving off a cliff. You're like in a stunt movie. And it says, oh man, you're like a motorcycle driver and you just like drive straight off the cliff. It sounds like your life expectancy is small. Or this is a small cliff?
It's all CPI these days.
It doesn't look like a very small.
You don't drive off anything at all.
50 meters, whoa. I think you're dead. Oh well, anyway.
Good luck, Herb.
Anyway, let's pretend you didn't die. So it says, you drive off the cliff, it's 50 meters. How fast must you leave the top to land at ground level 90 meters from the base? So your goal is to like hit this specific spot that the director told you to hit. So that you look,
We're only putting a pad.
yeah, you've got one shot to do it. Okay, so it's pretty important to get this right, I guess. So I understand why this is a physics problem. Do you guys? Pretty important to get it right. I don't think it's a real problem, but it's fun. So the cliff, what'd they say, 50 meters? Okay, we're driving off up here, right? So that's like us on the motorcycle. Such a masterful drawing. Okay, where did my markers go? I'm losing myself. Okay, what else did they tell us? The only other piece of
90
info.
meters that we can land at.
So this, where we're supposed to hit the target over here, that's 90 meters. That's all we know. And the question is what? How fast?
Don't have to buy.
So that's the what? What should I put that as? What are we looking for? V naught, right? Or VI?
So we're gonna be using some gravity.
We want the initial velocity, is that correct? Did they ask us for anything else? I don't think so.
Gravities.
I don't think so. I don't think we need to do anything. So let's split this. We just learned about vectors, right? Why do you think this wasn't in the first chapter? Because what? We're following like it's like two-dimensional motion, right? So I think that let's just think about it separately in 2 dimensions. Let's think about what's happening horizontally. And then over here separately, let's think about what's happening vertically. And let's look at our kinematic equations, same ones we used in the last chapter, no difference, okay? If we're thinking horizontally, what variable do you think we're gonna lose for distance? X, Y, Z, X. Yeah. So you guys tell me which kinematic equation might be useful. Go ahead and look at your list. Because you need to be able to select appropriate ones. That's the hardest part of this whole thing, is figuring out what am I looking for, and which equation do I use, and do I have to use more than one? Okay? Go back to your equation list and tell me which one do you think you want. Think about what we're looking for again. It's the initial velocity. Think about our initial velocity. Is it just a velocity, or is it just an x, or just a y? When you go off the cliff, what's happening? Do you have any vertical velocity? Right at that spot, right at the beginning? So really, can we make this a little more specific? Shouldn't that just be Vx? So you need to find an equation that you can pull out the initial velocity from. There's a couple different ones, right? We know acceleration, don't we? Or do we?
Yeah.
Yeah, it's changing from negative 9.8.
Acceleration's negative 9.8, period,
Oh,
right?
Yeah, yeah.
Is it, what about in the x direction though?
There should be no acceleration.
Are you accelerating in the x direction? We're assuming no. Like once you leave the cliff, can you step on the gas and accelerate? So in this situation, can you accelerate in the horizontal? No, so I'm going to argue, if you guys haven't figured it out yet, which is okay, let's use this. What is that one? V sub O x
Yeah, for time.
t plus 1/2 a sub x. Remember, we're working all in x, all horizontal here, right?
Squared. Well, times.
Times squared, okay. Let's just see what happens there. We'll worry about that later. Maybe we don't even need it, I don't know. Maybe we don't, sometimes you don't. Okay, so what do we know here? Do we know the initial x position? Well, let's think about it up here.
0.
Let's label this x 0, isn't that just 0?
Yeah.
And then down here, xf is 90, and that's just another name for this, isn't it? Could have written it to begin with. We good with that? We don't know that, well, this is what we're looking for, right? So we don't know that. Do we know the time? Do we know acceleration in the x direction? Yeah, we just talked about it. What is it? 0, right? That's 0, so this just goes to 0, doesn't it? So what's left? Let's just see. So if we plug in 90 here, we plug in 0 there, we got v sub 0x and t. There's still two things we don't know. Darn it. But the thing is, we haven't used all our resources here. We've only used what? We've only used our horizontal resources. We can still look at the vertical aspect of the motion and see if we can get something out of that. And in fact, without even thinking, I'm going to say, I'm just going to use the same equation, except I'm going to write what? Yeah. Y initial plus velocity at the beginning in the y direction plus 1/2 acceleration in the y direction. It's the same equation, just applied only up and down, is it not? Nothing else has changed. So let's see what we can get out of that, yeah? What's the initial, and I mean you can label, I like to label this on my picture too. What's y0 here? Before even picking those equations, sometimes if you're really having trouble picking the equation, put more labels on your picture and then you'll know more stuff you can plug in and you'll know which one to use better. That's another thing, okay? What is the initial y height? 50. What's the final y height? 0. What's happening with acceleration in this situation? You guys said in the y direction, gravity is always happening, right? We said before in the x direction, nothing's happening acceleration-wise. Okay, questions? Just plug it. So we've got what? Sorry, I keep holding my back. I'm
0,
hurting for some reason.
50.
You're going to be stopped. Well, I mean, it doesn't actually matter what your initial velocity is, because everything,
Your
you
initial
still take the
velocity
same amount of time to
0.
fall.
So we have to think. This is the hard part of physics right here. But you guys are getting it, right? Jake just said what? Say it again.
Your initial velocity down is 0. Just going horizontal.
You guys clear at that? At the top of the cliff, do you have any velocity this way? No, your velocity is purely
Horizontal.
this way, is it not? There's none this way. So v sub 0y is what? 0, so that whole term is gone. That I think will help. Plus 1/2 what? Negative 9.8. T squared. How many variables? 1. And oh, it's the one we need for over there. Wow. That's awesome. Negative 50 equals, that's going to be negative, right? Negative 4.9 t squared. So t is going to be 50 over 4.9 square rooted. What's that time? 3.19. Okay. Seconds? I think we were all working in seconds here, right? So when we take that, we stick it right here, and I think we'll get our answer.
So what does t mean, like time?
The time that you were going from here to
That's how long it's going to take.
there. Yes. So here's your little path. What kind of shape do you guys think this path has? It has a shape that looks like that, right? With a bend in it. What kind of mathematical function is that? Parabolic. It turns out in motion, when gravity only is involved, any thing that falls or jumps off a cliff like this, the motion is always parabolic. So we're going to be talking about that. There's a proof in the book, and we're going to do a little study on a little video project on it, I think. Why is it always parabolic? Anyway, so you plug that in, and you get 90 equals times that, so just divide by that, and you get how fast that person had to drive off the cliff.
28.17
So you move with 0.19
meters per second.
Significant with significance in there. What do you think? We had 50. We had what else? 90 meters. I think I'm just going to say 28.
Yeah.
Okay. Units. It's a velocity.
Meters per second.
Meters per second. Okay. Now, if you were asking, like, I saw a few people a little bit confused about, like, when we said this. Everybody okay with this? Like, during this entire trip, that does not change, right? Because this is all about constant acceleration. Gravity is there the whole time. So in the y direction, you're always going to be pushed on gravity. Gravity's pushing on you the same amount that whole trip. We good with that? Is everybody good with this? Because I don't think that we were. Why is the acceleration throughout this whole trip 0? Back here,
Unless they build a ramp.
could there be some acceleration in the X direction? Yeah, he's pushing on the gas, right? But as soon as you hit the edge of the cliff, what happens? Does pushing on the gas help anymore? No, so are you accelerating in this direction at all anymore? No, that's why it's 0 for this whole trip. Now back there, no, it's not 0, but we are only considering between these 2 points, not before them. That's why whenever we do a problem in physics, there's this notion of a system, okay? So in this system, the only places we're considering are here and here. Stuff that happens before or after that is negligible. We're focusing on those 2 places, okay? So, I hope that helped. I think we'll stop there for today.
What are either deceleration because?
I'm not sure.
Yeah, but it's so slow that we don't.